So welcome everyone. Welcome to this BGS interactive quiz. So the title of this was a little bit of a wordplay to do with rocks. So it's an interactive quiz and it's nice, tough and a bit wacky. It's usually pronounced whack, but a nice, a tough and whack are all different types of rock. A nice is a metamorphic rock, a tough is a volcanic ash deposit, and a whack is a sort of mud or muddy limestone. So yes, welcome. I hope this is going to be enjoyable and also slightly educational. So we'll start the proceedings. So welcome. Rules of the game. So there's only going to be a handful of questions. All of these are multiple choice. And the idea being that we're going to have a few rounds, as it were, a few different rounds. We're going to talk about, firstly, to do with geological time and the sort of vast amounts of time involved in all of the Earth history and sort of key things that have happened in there. We're going to focus in a little bit more to do with rocks in general and different types of rocks and what they mean. And then, because this is where I'm based, the headquarters for BGS in Nottingham, I'm going to talk a little bit about sort of the local rocks and a little bit of sort of questions to do with that. So if you're local, these will be specifically stuff that you'll have seen wandering around the city, for instance. So an initial starter, and I really like asking this question because it's a really good idea to sort of get an opinion on what people think, and hopefully try and give you a few ideas as to what the point is. So what's the point in geology? So we have a geological survey. It's the oldest geological survey in the world. It's the second oldest sort of organised geological body in the world after the Geological Society of London. What's the point? We have pushing a 200-year history. What's the point in geology? Why? Why look at rocks? Why look at dirt? So I'll give you sort of a few seconds to have a think about that. But what is there to be gained from looking at, say, the land surface or the rocks at the surface or the rocks and sediments beneath the surface, and they're getting deeper and deeper and deeper? So I'm hoping you'll immediately be thinking like, oh, well, what's the point of geology? We can get useful things from the ground or on the surface. So we could get sparkly minerals. We could get diamonds, cool, sparkly, nice jewelry things. So that's quite a common one that people will mention. And then sometimes people will mention things like, oh, well, if you want to build a house or a road, can the material you're building on take the weight? Can it take the properties of what you're trying to do with it? Those are kind of sort of common answers. But there is a whole host of other reasons. So both of those are completely valid and perfectly right. But there are other things like, very commonly, locally, drinking water. So the sandstones that we have in the city have been designated by the Environment Agency as something called an aquifer. And an aquifer is a rock that holds water. And it's immensely important across the Midlands, up into sort of the northeast, slightly into the northwest as well. So rocks can provide water. We can build on them. Are these rocks capable of withstanding the things we want to build? Can we tunnel in them? Do we have to do any special engineering things to tunnel into them? There's other things like we may actually want some of these materials to build with. So we have lots of historic buildings that require specific types of rocks. Thinking a little bit more sort of new and sort of the challenges we're dealing with today, we can think about climate change. Can we use rocks and our understanding of rocks and where they are to help mitigate against climate change? And the answer is absolutely yes. There are things like ground-sourced heat. Can we actually take heat from the ground and use that to heat our houses, our industries? Can we store energy underground? So pressurized caverns or heat again. And also things like rather technical sounding thing called carbon sequestration and storage. Can we actually take carbon dioxide from industrial processes and actually store it underground to try and mitigate against our footprint? And then there are kind of sort of more general things like, an understanding of geology gives us an understanding of what's happened in the past. Can we use that to predict what's going to happen in the future? And there's also a sort of general science interest that it's always really cool to find out about, dinosaurs, volcanoes, etc., etc. So a whole host of reasons to be interested and involved in geology. So I'm hopefully warmed you up a little bit as we go into round one, so geological time. So I'm going to ask questions. They're going to be multiple choice. There's going to be a little timer. You'll have 10 seconds, and then I'll give you the answer. So, question one, and you'll have to forgive my really noddy attempts at sort of little diagrams. Don't judge me too harshly. So, how old is the Earth? How old is the Earth? A, B, or C? Is it about 800 million years old? Is it about 2.5 billion years old? Or is it about 4.5 billion years old? So that's your 10 seconds. The clock's gone red. And the answer is 4.5 billion years old. So the Earth's actually quite old. In the context of the universe, I think the universe is about 12.6 billion years old. So the Earth has been around roughly, we think, about a third of the time that the entire universe since the Big Bang. So a lot of time to have all sorts of geological processes happening, forming rocks. So here's a good one. What is the name of the geological period in which T-Rex lived? So, just nabbing the classic film logo. So, Jurassic Park, Cretaceous Park, Triassic Park. So obviously the geological periods are either A, the Jurassic, B, the Cretaceous, C, the Triassic. Any thoughts, any comments? And it seems really obvious, doesn't it? I mean, the logo has a skull of a T-Rex on it. It's Jurassic Park. But it isn't. So always a slight bugbear for me as a geologist. The Tyrannosaurus rex doesn't belong to the Jurassic at all. It's actually very late in the Cretaceous. It's actually a good period of Earth history after the Jurassic. But again, it's a really cool fossil with lots of pointy teeth, so that's probably why they used it. So, keeping with the theme of T-Rex, and this maybe sounds a little bit of a complicated question, but if you measure the time between A, Tyrannosaurus rex, and the first bird, the first evidence of recorded birds, that's a photo of a fossil called Archaeopteryx. I think that's specifically the one they have in the Natural History Museum in London. Questionable whether it is the first bird now, but it's good for our approximations. So the time between Tyrannosaurus rex and the first bird, is that longer or shorter than the time between the iPhone and T-Rex? So which is the shortest amount of time? So it goes iPhone, T-Rex, first bird, which between that sort of first bird and T-Rex, or T-Rex and the iPhone, which is the shorter? So 10 seconds. Almost seems a bit crazy, doesn't it? So clock's gone red, and I wouldn't include it unless it was the answer. So maybe you could sort of play the quizmaster of this. But actually, T-Rex is closer in time to the iPhone than it is to the first bird. And to sort of give you an idea of that, there's about 65 million years between T-Rex and the iPhone, and there's about 85 million years between the first bird and T-Rex. So about 20 million years difference. So yes, the idea of geological time could sometimes be quite confusing. So this is an example of the internationally recognised stratigraphic chart of the sort of ages, geological ages for the Earth. So some of you may be familiar with this, some of you maybe won't. You'll see some names on there: Triassic, Jurassic, Cretaceous, etc. That hopefully makes sense to you, or you maybe heard of before. But there's something interesting with this chart, and I'm going to show it again, but I'm going to show it to scale. So what I'm going to do, if the PowerPoint works well, is on the end of the screen, there's a couple of bars that says era and system/period. So these are different sort of hierarchies of ages, of geological ages. And I'm going to have it sort of scroll across the slide. And as it's going through, I'm just going to highlight some sort of what I think are interesting events in sort of Earth history. So in about 4.6 billion years ago, so GA is a sort of shorthand for billion years, the Earth is formed. Shortly afterwards, a few hundred million years afterwards, maybe even sooner, the moon forms or starts forming. It takes about sort of 4.3 billion years ago before we get our first water. About 4 billion years we get our first fossils. Now these aren't necessarily fossils, these are more chemical evidence of organic activity, so not really true fossils. About 3.6 billion years ago, we get our first sort of single-cell organisms. So these are the actual sort of fossil evidence of single-cell organisms. It's only a few hundred million years later that we get our first sort of photosynthesizing organisms. About 2.5 to 2.7 billion years ago, we have our first sort of oxygen-producing organisms. Now, these are really important because these are the first sort of the drivers of huge change on our planet. About 2.2 billion years ago, we have our first evidence of an asteroid impact, which is interesting because there's a lot of suggestions that the moon formed from the Earth as a result of an asteroid impact that sort of blew parts of it away. So it takes all this huge amount of Earth time. So billions, we're now coming up to about 550-ish million years before today. So for that sort of 4 billion years, a huge amount's happened, but there's an absolute explosion around the Cambrian times, and you may have heard this term, the Cambrian explosion, about 540 million years ago, where life just seems to suddenly almost get rocket fuel and change massively, and a whole host of weird and wonderful creatures and organisms appear. So it's our first big sort of mass extinction and explosion. I say explosion as in not an explosion. We say an explosion of life. So life has started to take on new forms. It's starting to evolve. You have weird creatures. Organisms start to develop their first shells, their first teeth. Land plants start to colonize the Earth, sort of at the start of the Devonian. During the Devonian, it's kind of the key period for sort of the colonization of land. We get our first trees, our first insects. It's only in the sort of Carboniferous where we start to get sort of reptiles. These aren't necessarily reptiles like we would see today. There's early reptiles. And then it's only in the sort of Cretaceous that we get our first flowering plants. So only sort of 70-ish million years ago that we had plants. I mean, that's crazy when you think the Earth is 4.6 billion years old. As question before, T-Rex comes towards the end of the Cretaceous. Humans, you can see where that arrow is, very, very close to the sort of modern. So each one of these blocks is to scale. So only really, really recently as sort of apes and humans appear, and then there should be an arrow right at the end saying, obviously, ultra modern today. You're listening to this talk. So yes, so that's what it looks like to scale. Huge amount of difference. So round 2, rocks and sediments. So question: what do we call rocks that are made from molten lava and magma? So choice A, B, C. Are these sedimentary rocks? Are they igneous rocks? Or are they metamorphic? Any thoughts? So hopefully that's not too hard a one. I'm hoping that you identified it correctly, that these are igneous rocks. So sedimentary rocks are generally made up of pre-existing bits of stuff, other rocks. Igneous rocks are formed from magma and lava, and metamorphic rocks are sedimentary, igneous, and potentially other metamorphic rocks that have been changed through combinations of heat and pressure. So question 5. What are sand grains made of? So, are sand grains made up of quartz, glass? Are they made up of shell fragments? Or are they made up of anything? Excuse me. So, potentially slightly cheeky question. In some ways, it's actually all of them, but the best answer is actually anything. So this always makes me laugh, that sand and sandstones are not defined by what they are made out of. It seems like a bit of an odd concept. So a quick screen grab from Google. Sand is actually based on the grain size of the pieces in the material. Doesn't matter what they're made of. So if I just highlight, and this is why you should always be careful when you use Google to research. So Google says that a sand is a loose granular substance, correct? Typically pale, yellowish brown, resulting from the erosion of silicious and other rocks, blah, blah, blah. So the colour bit I have a problem with, but it's not that bad a description. It's not too bad. This one, it's sort of second description, a light brown colour of that of sand, absolutely wrong. Really dislike that. However, the Wikipedia entry is bang on. Sand is a granular material, composed of bits of rock, blah, blah. Sand has various compositions, but is defined by its grain size. So, next time you see your friends go down the pub, I don't know, and you want to say, you can ask them, what is sand made of? Sand is any material that is between 2 millimeters in size, so just looking at this chart, and roughly a 1/16 of a millimeter in size. Anything between that range in sizes is a sand. The reason I have such an issue with the colour, here are some awesome pictures of some beaches, so one from Hawaii, which is made up of olivine sands. So you can see wonderful, cool, dark green colour, and then another image from Crete, which shows pinkish colours, and these are broken bits of coral and other shells. So colour can be anything when it comes to sand. So, next question. Which of the following of these isn't a real mineral? And if you know anything about the way we name minerals or some names of minerals, some of them can be really quite strange. So, more choices this time, 5 choices. So, is it A? So, which isn't the real one? Carnallite, mullulite, eureka dumpite, amazingite, and welshite. Be very, very careful where you put the syllable there. So which one of those isn't real? So that's your 10 seconds. So unbelievably, amazingite. I couldn't quite think of what to put, but amazingite is the actual one that isn't real. The others are. And this is really weird. So you find minerals all over the world, and they tend to be named after either the person that has first discovered them or the place they've been found. So a really good example. So mullulite is actually from Mooloo in Australia. Eureka dumpite is a mineral that was found in America, and it's from the Eureka Mine dump site. Eureka dumpite. Yes, all sorts of weird and wonderful naming conventions. So round 3. So fast coming up to the final round. Nottingham, right. So if you've ever been to Nottingham prides itself on the city of caves. There's lots of caves, and these caves are dug into rock. And if you've ever been to the castle or sort of wandered around, you'll see there are bits of rock, so bits of sandstone sticking out of the ground. But where did those rocks originally come from? So before they were rocks and they were loose sediment, that loose sediment came from somewhere. So did they come from A, Scotland, B, France, or C, Germany? Any thoughts on where they came from? So, rather randomly, the sediment that made the rocks locally actually came from France. It actually came from sort of northern France, probably around Paris, a little bit further north. And these sediments came from northern France, came sort of to the Midlands. I'll talk about how in a minute. But what do you think the weather was like during this time? And I'll give you a clue. It's actually deposited during a period called the Triassic. So, what was the weather like? Was it really hot? So this is my attempt at Goldilocks. So not too hot, not too cold. A colleague said I should call it Goldie Rocks. Or C, was it cold? So was it hot, okay, so not hot, not cold, or cold? So what was the temperature like when this sediment was coming from northern France? Was it hot, not too bad, or cold? So that's 10 seconds. So it was actually really, really hot, a really hot period in Earth history. So I mentioned the Triassic because the geological age before it, the Permian, even more so, and then into the Triassic, were extremely hot periods in the general sense in global Earth history. Really, really hot. some localized areas which were cooler, and potentially some areas which actually had glaciers. But in a sort of global context, it was very hot. So we've said they came from France. We've said it was hot at the time. But how do you think the sand grains, so the sand grains that would eventually become the sandstones in the city, the tunnels and the caves are built into, how did they get to Nottingham? And there's lots of ways you can move sand grains, sediment around the earth. Do you think it was by the wind? So the technical term would be aeolian deposits, rather an unusual word. B, do you think it was ice? Or C, do you think it was water? So 10 seconds. So one of those was responsible for bringing the sediment from France to where we are in the Midlands of Nottingham. So any thoughts? So I'm hoping you immediately discounted ice, given I said how hot it was. So yes, it was water. Very much water, which seems a bit odd. It was water via rivers, huge rivers. And if I show you some rather sort of well-known sort of geological... So these are maps, these are called paleo-reconstructive maps of what the Earth would have looked like. And this is specifically around about the time that the rocks are being deposited locally. So the rocks locally are actually from a group called the Sherwood Sandstone Group. Great local name. And if I just highlight, sort of outline where sort of mainland England, Wales, Scotland is. So France is actually just to the south of that, and you can see there is no water, there is no ocean, there's no English Channel, there's no North Sea. And this area of northern France was really high. And because it was really high, it rained a fair bit just because it was colder, cooler. And as it rained, those mountains slowly got eroded and they sort of shed material. And that water also helped form rivers. And these huge rivers flowed from northern France across a dry English Channel and then deposited the rocks all over sort of central southern England and then spread across the Midlands and also as far north as York. So, huge rivers. And these rivers would have looked something like, if you look on Google Earth, something like the Ganges, the Brahmaputra Ganges. These rivers would have been absolutely enormous. So even though it was a very hot desert landscape that didn't have much vegetation, much trees, much wildlife in general, these rivers would have been huge, potentially a few kilometres wide, maybe even sort of 10 kilometres wide, so about 6-7 miles. So absolutely huge rivers, massive rivers. And that's it. That's the quiz. That's the quiz. I hope you found it good. I hope you found it entertaining, interesting. So, importantly, how did you do? So there were only 9 questions. I probably should have thought of another one to make it a round number. But if this was in person, and I'm really pleased that you managed to check this out remotely, but I would usually get people to clap or cheer or jump up as their score was reached. So I'm just going to get this little timer, sort of like rev meter to move. So even though I'm not there and I can't hear you, you must clap as it gets to your number, cheer, whoop, holler. So hopefully you did well. Hopefully you've maybe learned something. Obviously, if you did get them all, then you should absolutely look at the BGS website and apply for a job. But I hope you found it interesting. Thank you so much for tuning in, for checking this out. Yes, thank you very much. And I hope it was good. Thank you. Bye.